Have you ever just stopped and looked around at how everything is constantly changing? I mean, a puddle dries up, a log crackles in a fire, an old bike gets rusty. But here's a question. Are all those changes really the same deep down? Well, today we're going to dive into that. We're going to solve a fundamental puzzle about how stuff transforms. And you'll see there's a world of difference between a simple change of costume and a total identity switch. Okay, so let's jump right in with our two main suspects. On one hand, you've got something we've all seen a million times, a block of ice melting into a pool of water. Simple enough. But on the other hand, you have something way more dramatic, a bright, shiny strip of magnesium metal bursting into a blindingly brilliant flame. And when it's all over, all that's left is this crumbly white powder. So clearly, in both cases, something changed. No doubt about that. But are they the same kind of change? Is what's happening to the ice the same as what's happening to the magnesium? That's the mystery we're here to solve. To really crack this case, we have to go undercover. We need to look deeper than what our eyes can see, because the real secret, the clue that unlocks this whole thing, isn't on the surface. It's hidden in the tiny world of atoms and molecules.
Yep, it all comes down to the particles. To really tell these two transformations apart, we need to zoom in, like way, way in, and see what the individual molecules are actually doing. That's where the story gets really interesting.
All right, our first key piece of evidence is this idea of a physical change. Think of this as a superficial change. It's like getting a haircut or changing your outfit. You might look different, the form has changed, but you are still you. The substance itself doesn't change its core identity.
And on the flip side, we have a chemical change. Now, this isn't just a new haircut. This is a fundamental transformation. The original stuff is literally gone, and in its place, something completely new has been created, with totally new properties. The character has been completely rewritten. Okay, now that we have our definitions, let's put them to the test. Let's open up case file number 1, the melting ice. We'll call this one the shapeshifter. The big question is, did the substance actually change who it is? And here's the inside story, what's happening at that molecular level. When it's solid ice, the H2O molecules are all locked up, vibrating in place. When you add some heat, they get more energy, break free, and start sliding around as liquid water. But, and this is the absolute key, they are still H2O molecules. They haven't changed their identity one bit. And you see this pattern everywhere with physical changes. When you boil water, the steam is still H2O. When you dissolve sugar in your coffee, the sugar molecules are still in there, just mixed in. Heck, even if you crush a soda can or shred a piece of paper, you're just changing its shape and size, not what it's actually made of. All right, time to tackle our second case file, that spectacular burning magnesium. Let's call this one the alchemist. Is this just a simple costume change, or is something much, much deeper going on here?
You know, the absolute best way to picture a chemical change is to think of atoms as little Lego bricks. Before the fire, you had a pile of magnesium Legos and a bunch of oxygen Legos floating around in the air. The fire was the energy that broke them all apart and let you rebuild them into something totally new, a structure called magnesium oxide, a new substance.
So if you're playing chemical detective, how do you spot one of these transformations? Well, you look for the telltale signs. Did it change color, like metal rusting? Did it start bubbling, producing a gas? Did a solid suddenly appear out of two liquids? And of course, the big one, was there a dramatic release of energy, like that bright light and heat from our magnesium? These are all your clues.
So, we've examined the evidence, we've looked at the crime scenes, we've gone down to the molecular level for both of our cases. Now, it's time to deliver the verdict. And it all boils down to this one single defining difference. This is the smoking gun. A chemical change always creates a brand new substance. A physical change never, ever does. That's it. That's the test. The ice became water, but it was still H2O. The magnesium became magnesium oxide, a totally different thing. This table here just lays it all out perfectly. Look at that very first row. New substance formed. For a physical change, it's a hard no. For a chemical change, it's a definite yes. And that also explains why physical changes are usually easy to reverse. You can just freeze the water back into ice. But chemical changes are tough. It's really hard to unburn a piece of wood. Now here's a really cool little twist that builds on our Lego idea. Even when it looks like something has vanished in a chemical reaction, like a log burning down to just a little pile of ash, not a single atom is actually lost.
It's a fundamental rule of the universe called the law of conservation of mass. All the original Lego bricks are still there. They've just been rearranged into new things, like ash and smoke and gases. The total weight, the total mass, stays exactly the same.
So, okay, physical, chemical. Who cares, right? Why does any of this matter outside of a science class? Because it's happening literally all around you all the time. Frying an egg in a pan, that's a chemical change. Boiling the water for your pasta, that's a physical one. Understanding the difference is just, well, it's understanding how the world works.
And that whole reversibility thing really gets to the heart of it. Think about it. Melting ice is like rearranging the furniture in your room. It takes some effort, but you can easily put it all back. But burning a match, that's like baking a cake. You've broken down the eggs and flour and sugar and rebuilt them into something new. There's no way you're getting those original ingredients back. You can't just unbake a cake.
All right, I want to leave you with a final puzzle to chew on. We said that a big burst of energy, like heat or light, is a really good clue for a chemical change. But it's not foolproof. It's not 100% proof on its own. So my question for you is, why not? What common physical change also involves a massive amount of energy? Use what you've learned today and see if you can crack it. Thanks for tuning in.